All right, we have 113 adults. They have a medical problem. Obviously, the doctors are trying to cure that medical problem. So the outcome is either they're cured or they're not cured. Two different predictors. The first is they've had intervention or they've had no treatment. And duration, the number of days before treatment that the patient had the problem. All right, so let's go ahead and start looking at this output. Logistic regression, you can watch the SPSS video, but I have some slides here for you to kind of look at to be able to know what to choose and whatnot. All right, first piece of our model. This first table here is really just telling us how our variables were coded. Now this is going to be very, very critical because we are going to have a coding. And understanding how to read and identify what SPSS did to your data is going to really help you be able to understand the output. So this is how SPSS has decided to code it. And then this is how they've decided to code the predictor. So we have intervention. No treatment has a 0 value and intervention has a 1 value. And we can also see that we've got frequencies. How many had no treatment? How many did have intervention or some type of treatment? Sometimes if you're doing a deviation coding, which is an option in your regression, you're going to have a -1 and a 1. Those are going to be your parameter codings. If you did a simple contrast, you're going to, simple contrast is -0.5 and a positive 0.5. So you should be able to tell what type of model you're running just even looking at this screen. All right, let's go ahead and look at our next piece of output. All right, this first piece here, we have step 0, and step 0 had 3 iterations. What's important is this -2 log likelihood. So that is essentially the log likelihood of our base model. So that is with only a constant. And you know it's only with a constant because here it tells you what your coefficients are, so you only have a constant. So that log likelihood is equal to 154.084. All right, the next, and this is what we're going to compare everything else to. So again, very similar to regression, the base model is just using the mean value. Well, this base model is just having a constant variable in there. This one down here, this next table, shows that we have, in step 0, the predicted values of not cured are both 0 if the observed values were, so this is, if the observed value is not cured, the predicted value is not cured. If the predicted value, observed value is not cured, and the predicted value was cured, everything over is in cured. So we have 113 data points, and either everybody is cured or everybody is not cured. So essentially we have 48 divided by 113. We have 42% that is not cured, and we have 58% that is cured. So what happens with this model is they're going to move forward with this information and they're going to say, all right, 58% is better than 42%. So cured is a positive, that is a correct probability assumption. Not cured is not correct. So the cured, that's a 58%. So we're going to go ahead and classify 58% of our data is correct. I don't know about you, but that's a pretty crappy model. But again, it's just with a constant in there, so it's supposed to be a bad model, and hopefully as we go forward into step 1, we'll end up with a slightly better model. All right, what was in the equation? Again, it's just that constant, so it's really not telling us too much. This is telling us, next table is what was not in the equation. So we had intervention, duration, and duration by invention. And these overall statistics is nothing more than our residual. You can also think of it as our chi-square. Our chi-square statistic. So in the variables that were not added, intervention would have been added first because it has the largest value. The significance, it's saying it is significant, so again it would be entered. Duration by intervention, so the combination of the two, it is significant, so it would be entered. But duration, it's by itself, is not significant, so it would not be entered. And so the overall chi-square tells us that it is significant. So the coefficients that are not in the model are significantly different than 0. So what does that mean? That means a big asterisk. All right, the addition of one or more predictors will improve our model. So it's going to improve that predictive power, which is exactly what we want. All right, let's look at the output for step 1. Now there's a lot of information here. All right, so step 1. What is in step 1? Well, we figured out before that the first thing it's going to put in is intervention. So that's what's in step 1. So the first thing to note is let's go down to our classification table. And it says that the model predicts that all patients with intervention were cured. So 57% 57 had intervention. All right, so if we look at the bottom here, we see that we have 2 incorrect variables. That is incorrect, not cured, that's not right, and cured, not cured is incorrect. So the model is perfectly correct for 41 out of 57. So that's a 64.6% overall. With the model and the constant, the model was only 57.5% correct, so this is better. So this is a better model. Simply because that 64.6 is greater than 57.5%. All right, and actually 41 divided by 57 gives us a 72% correct, so that's pretty good. All right, so moving on to our log likelihood. So our log likelihood, we had, the smaller the log likelihoods, the better things are. So our previous model had 154 and some change. So this is a reduced log likelihood value, which says our model is better at predicting. So our model prediction improved. And then we can look at this chi-square. I know it seems like we're jumping all over. So the first thing we looked at was this table. And it said that prediction seemed to be better. The second thing we look at, so we're working backwards, upwards. Second thing we looked at was that log likelihood value. And then the last thing we're going to look at is the chi-square value, which is assessing the change in the model. So that's the change in the model from the model with a constant to the model with intervention. So that is the log likelihood of the model minus the log likelihood of the baseline. Gives us 9.926. It is significant. So we can say the model is significantly better. All right, so that was the third thing we looked at. All right, we could look at our odds ratio, and unfortunately this is something that we actually would have to go ahead and calculate. As bad as that may seem. But we're going to go ahead and do that here in a second. All right, the next piece is the variables that are in our equation. So this is step one. So again, here we have intervention is the only value that's in the equation other than the constant, because we always have a constant in the equation. First thing that we're going to look at is the Wald statistic. Oops. We're going to look at this Wald statistic right here, and that's going to tell us whether the beta is significantly different than 0. Obviously, if it is, the predictor is going to make a significant contribution. But we do have some concerns here, is if our beta is large and the standard error is inflated, this will underestimate the Wald. But these beta values do not seem to be very large. They seem to be very reasonable. The data seems okay. So then we'll go ahead and look at our significant. And it is significant, so we can go ahead and say intervention is a significant predictor, which is good. We also want to make sure that it does not cross 1. So with regular regression, we don't want it to cross 0. Here, we don't want it to cross 1. If it does, that means as the predictor increases, the outcome decreases, which is really not what we want to have happen. All right, then the next thing we can do is we can go ahead and calculate that odds ratio, which is really the critical piece of this. So if we want to know what the probability of a patient being cured given that they didn't have the intervention. So that's going to be the probability of cured, and that will equal, we have to actually calculate this, unfortunately, 1 plus e to the negative b0 plus b1 x1, and we know that is equal to 1 over b0 is that negative 0.288 plus b1x 1.23 essentially. And this goes back to that first coding. if they did not have intervention, the no treatment parameter coding was 0. So that x turns into 0, which means this variable ends up with 0.428. So the probability of them not being cured is equal to 1 minus p of cured, right? It's just the remainder is 0.572. So the odds ratio is 0.428 divided by 0.572, 0.748. All right, so that is the before picture. Now we have to also calculate the after picture. So no intervention is before. So let's say they did have the intervention and they were cured. All right, so the probability of the patient being cured with intervention that's going to be equal to 1 over the same thing, 1 plus e to the negative 0.288 plus 1.23, except this time intervention had a parameter of 1. So we go ahead and calculate that. That is 0.719. So the probability of being not cured is simply 1 minus that value, 1 minus 0.719, or 0.281. All right, so that gives us the odd ratio for the after case, 0.719 divided by 0.281 of a 2.559. All right, so then our change in the odds ratio is the after divided by before, or the 2.559 divided by 0.75. That gives us 3.41. All right, what does that mean? Well, that means the value is greater than 1. So as the predictor increases, and again, the predictor variable is intervention. So as you move from intervention, 0 intervention, to 1 intervention, so this is no treatment, one intervention is treatment. So as the predictor increases, so as we go from no treatment to treatment, the odds of the outcome occurring also increase. Now, if you'll remember, the outcome also had a coding variable. So that outcome coding variable, we also have to look back and say, well, what did that mean? So the outcome coding value was 0, no cure, to 1, cured. So as we move from no treatment to treatment, we are predicting that the odds of the outcome moving from no cure to cure is also increasing. So the odds of the patient who is treated being cured is 3.41 times higher than those not being treated. So that's what that odds ratio is telling us. So that's pretty critical. All right, so I think that's the most important piece of output almost in the entire jazz there. All right, let's look at what happens if we were actually to remove intervention. So logistic regression puts their variable in, and then they go ahead and remove the variable. So all we look at is 0.002, and that tells us removing the predictor has a significant impact. Right? So removing So if we remove it, it has a significant impact, which means we don't want to remove it. All right, then we look at the variables that are not in the equation, and we look at their significances. Well, they are all not significant. So this is essentially telling us that we should not add these variables because they're not going to make an impact in the model. So it looks like the only term that we really should have in the model is the intervention. All right, so let's go ahead and look at our classification plot. And our classification plot is just a histogram of the predicted probabilities of a patient being cured. If a model is perfect, all cured would be over here on the right, and not cured would be over here on the left. So we would have more cases cluttered at the end of each graph. So the more they are at the end of each graph, the better the model is. If everything is clustered at 0.5, this essentially gives you a 50-50 chance of predicting everything correctly. Well, instead of wasting your time, why don't you just toss a coin? Because you're going to get the exact same output. So we want everything to be a little bit skewed further to either end of these spectrums. What it looks like is we have all cured would be over here, right? Because cured has a 1. That's how it was coded. Not cured is 0. So when you look at this, as you move toward the right, you should end up seeing more and more cured patients. But it looks like we've got 3 non-cured in there. And as you move towards the left, we should have not cured. And it seems we've got some cured patients there. So those 2 that are circled are our mispredictions. And it looks that the model for the not cured on this side is nearly not as good as the model that we have for the cured piece. So we're able to predict the cured cases fairly well, but we're not able to predict the not cured pieces. So the good model of the cured cases predicts pretty well. All right, so that's pretty much it. It's a fairly decent model using intervention. So we've got not as much output as the multiple regression, but there's enough output. I think that's slightly confusing. But again, the most important thing is to find the odds ratio So we know that the odds of a patient who's treated being cured are 3.4 times higher than those that are not being treated. That is the ultimate outcome of this model. And that's really what we want to know. Should we treat somebody or should we not treat somebody in order to be able to cure them? And it looks like if they want to be cured, it's a 3.41 times higher probability of being cured than with intervention than without intervention. So that's the ultimate goal of logistic regression. All right, the last piece is multinomial logistic regression, which for obvious reasons we're not going to go over, because we would be looking at up to 9 different outputs to be able to figure out what the answer is. So it's breaking that outcome variable down into a series of comparisons. So that just makes understanding the output even more complicated. So instead of trying to complicate things too much, we just want to be able to understand how to do logistic regression and how to understand what its output is.